take a look at our first and foremost topic after introduction, that is existence and uniqueness of solutions. Now let's talk about what really matters. When we talk about differential equations, we need to find solutions. But if you are given an mth order differential equation, ODE, how do you know that there is a solution? There's an important theorem, or should I say two theorems, that will help you, put a bound to your uncertainty regarding the solutions. You can talk about two things regarding a solution. You can say that there is a solution, or at least one solution, or you can talk about its existence, or you can talk about its uniqueness. That is, there is just one solution. If you can talk about its existence and uniqueness of solutions, then you can say that there is just one solution, or there are at least one solution for a ordinary differential equation. And let's talk about these two theorems. The first is existence theorem. Existence theorem says that for a function such as this, y dash is equal to f of x, you agree that that's an ordinary differential equation, and for such a system, if you can say f of x or modulus of f of x is less than or equal to some constant k, and for an interval x element of A to B, let's say centering around x element of modulus of x minus x0 less than A, and modulus of y minus y0 less than B. So what is this? It says that you are establishing a region, not necessarily at 0, but centered at x0, y0, having a width of 2a, a width of 2b. This region is important to the existence of the solution. If we can establish such a region and then say that y dash, or let's say f of x, is continuous in this region, that is, there are no break points, and you can say that it is bounded in this region, that is, it has a finite value in all its points and a value that is less than k, an arbitrary constant, then you can say that there is at least one solution for y. This is the existence theorem. For more details, please refer to page 37 of Erwin Kreyszig textbook. It's given there, and we'll move on to our next theorem, the uniqueness theorem. Now we've established that you have a method to check whether a differential equation has at least one solution. Now that's just vague. Now if you want to find out whether the equation has no more than one solution, that its solution is unique. There's another theorem. Along with our constraints for the existence theorem, that is modulus of f of x comma y is bounded in a defined region R. That's the rectangle I drew before, and f of x y is continuous and we'll add one more criteria to this. If we can find fy of xy, that is the partial differential of f with respect to the variable y, and if you can say that in the same R, this is bounded to a value less than or equal to m, you can say that the equation y dash is equal to f of x has at most one solution. And so, if you can satisfy the existence theorem and satisfy the uniqueness theorem, simultaneously these two theorems imply that if you satisfy them, the ODE has just one solution. But these two theorems, they are sufficient conditions for the existence and uniqueness, respectively. They don't describe the converse is not always true. So, because they are sufficient criteria, we can boil down these two theorems to one specific equation. That is, if you have y2 and y1, and if you can say that f of x comma y2 y1 minus f of x comma y2 by mod of y2 minus y1 is less than or equal to some constant m that's bounded. Let's put in less than or equal to there. That's bounded, and if this y satisfies that, let's say then it says that the ordinary differential equation will have just one solution. Now we shall move on to another important part of this module called the Ron scale. Let's talk about the Ron scale. Those of you know about vector calculus, you know that if two vectors, vector A and vector B, are independent, or let's say orthogonal to each other, that is, we have vector A here and vector B here, their dot product would be equal to 0. Or let's say AX BX plus AY BY equal to 0. Now, how do you represent this in matrix form? This can be simplified to a matrix determinant AX, AY, BX, BY. So, let's take this example to our ordinary differential equations and their solutions. if you found two solutions, f1 of x y and another solution f2 of x comma y, how do you establish that these two functions are not dependent functions? That is, let's say there are two vectors in the x and y plane and they are perpendicular to each other. That is, for a more simplified answer, they form a perpendicular pair of vectors that can map to any other point in the entire vector space. That's a concept that we will face in your classes or maybe in the next semester papers, but sufficient or what we need to find out here is some way to represent the functions that in a way such that we need to find that f1 and f2 are independent solutions. And that's where Wronskian comes in. He's named after a mathematician, and he said that this is f1, f2, f1 dash, and f2 dash. Then the determinant of this matrix, if it is not equal to 0, then these two functions f1 and f2 are linearly independent solutions of our original ODE. It says that f1 and f2 dash plus f2 and f1 dash not equal to 0. This is called the Wronskian of the solution.